Welcome to Breadboarding. In this part 2 of video 17 in the series, what I'm going to be doing is taking the existing Nano Comp. Now we've upgraded the power distribution on it, and we're going to convert the address decoder to a programmable logic device. This is the block diagram. The only real difference between previous diagrams we see here, we've got the buffers that we added in the previous video. The address decoder, which currently is a fairly standard 74LS138, which is a 3 input lines to 8 output lines sort of decoder. So it's a binary 3 to 8 line decoder. We're going to be replacing this with a programmable logic device. To start with, we're just going to keep the existing memory map. So in previous videos, you'll remember we've got the 1000 range for the RAM, which is known as signal Y1, peripheral interface adapter 4000 Y4, the serial port or asynchronous communications interface adapter is at Y5, and then the ROM is at the top of the 32K address space that we're using from 7000 up to 7FFF. Now, this design is only making use of A12, A13 and A14. The A15 line is not being used at this point in time, although it's included in the address bus buffers. We're not making use of it in the decoder. So this should mean that the monitor ROM can be exactly the same as we had before. The only thing that's really changing is this chip, and we're going to be looking at how to program that. So programmable logic device, a PLD, also sometimes known as a GAL, generic array logic. Lattice Semiconductor, I think, first created these many years ago. I'm not sure you can buy GALs anymore, but the Atmel ATF22VL10 is a programmable logic device which matches almost identically the GAL. And what this allows you to do is to configure by config files how you want the inputs and the outputs to follow what those inputs are. Now, the PLD is quite a flexible device. It's got many different types of gates, including flip-flops and things, so you can build counters, you can build quite complicated decoders and various other things. I'm not going to go into all that now, just to say that the data sheets of these are quite complicated, and to learn how to program these in all its complexity is probably a whole series of videos on its own. I would have to say I've just used some of the examples I've found elsewhere on the internet, and I've adapted them to be used for this particular address decoder. And you can see here how we do things is there's a PLD file. This is just a text file. I tend to have things like pin maps and memory maps in there just for documentation. And then what you do is define labels for the pins and then rules that determine how the various inputs on the various pins are then combined in logical combination to produce an output. So we'll be looking at that in a little more detail as we go through the configuration of the PLD. And once we've programmed the PLD, we can just use that in our XG Pro EPROM programmer. We're going to fit it onto the board and just make sure that when we rewire the configuration, obviously the current chip I think is a 16-pin chip, and this is a 24-pin chip. So we'll have to move things around a little bit, but once we've put it in there, then basically everything should just work as we had before. So here we have a Atmel ATF22LV10CZ. The only thing, slightly unusual thing is they are the 0.3-inch wide, but they are 24 pins, so they're quite long and skinny. So here we have the PLD configuration file for what I've called NanoComp V3 memory map decoder. So this is just a text file, and all I've done here is documented the existing memory map. So we've got 1000 range Y1 is RAM, PIA is 4000 at Y4, the serial port is at 5000 Y5, and the ROM is at 700 and is Y7. In fact, we're only using 7800 to 7FFF. So what this shows here is this is how we've chosen to allocate the signals. We're only using the basic logic aspects of this chip, so we don't need some of the there are flip-flops and various other things that we could use in here, but we don't really need that. So all we're doing is we're taking the E-clock signal. We'll also take the read-write signal as well, because there could be some chips in the future that might need to be able to separate out the read and write signals into two separate signals. We then got A15 down to A8. We're not using pin 11, 13, 14 or 15. And then all I've done at the moment is just simulated the 74138, so all of the output pins Y0 to Y7. So it should mean that we can just wire these up pretty much as the existing chip is. And then we define for the inputs what the labels are we're giving to each pin. And then down here, this is really where the clever stuff occurs. These rules are fairly straightforward, but what this is basically saying is that the Y1 RAM should be enabled when A14 is low, A13 is low, and A12 is high. So this is the 1000 range, and also we need the E signal as well. The ROM is when we've got A14, 13 and 12. So these were the three address lines that were feeding into the decoder. So when they're 111, we get the ROM, and when they were 001, we get the RAM, and then the PIA and the serial port are in here as well. So these are the rules that we're using, and then the only thing is, because the chip selects are actually active low, then we're just using these values here inverted. So this defines the rules that tells us how to reproduce the current address decoder. So this is WinCUPL, WinCouple, however you want to say it. Now there are some bugs in this that whenever I open my files, when I have the project view open, then it just crashes and bombs out. So what I've found is that if I open one of the reference applications, you see here it has the project page here, although it's not populated with what we'd expect. What I can do is to turn off the project view, and then if I open my own file, then I'll find that it will open successfully. I just need to navigate to my PowerMac PLD, and I've got a number of versions here I've already done. So version 3 is the standard view that we've got for the current memory map, and so this is the file we've just been looking at, and all we need to do here is to run the device dependent compile, and that has compiled successfully. What that will produce, JED file. There we go. So for some reason, when it compiles a JED file, even if it says V1, V2, V3, it seems to only have 8 characters, so it truncates it to this. So all I'm going to do is, if I had a V3 before this, V3 JED, no, I don't think so. So I'm just going to rename this to V3. So now I've got my EPROM programmer here, and we've got our PLD chip. So I'm just going to plug that in to the programmer there. And now we're going to run up XG Pro. And you can see this has all already got the chip selected in here. And what I'm going to do now is to load the file. I just need to make sure I get it from the right folder that we've just burnt. This is the V3 JED file. This has loaded all of the config for that. And all we're going to do now is to program it. There we go, program successful. Now, one of the clever things that XG Pro can also do, which I haven't really talked about too much, is it's possible to test chips as well. And it comes with a load of rules for testing standard logic chips, but what you can also do is define your own. So this is one that I've done for this particular configuration. And when you set it up, what you do is define how many pins you've got, and you see that pin 24 is +5, pin 12 is ground. Then we can define which pins we want to define as 0 and 1, and then which pins we expect to be high or low, and those pins we don't care about. And what these rules here I've done is I've plugged in the various combinations of the read, write, and E signals and all the various address signals and which of the outputs we expect. So this is 0, 1, 2, 3, 4, 5, 6 down to 7. So if this has worked properly, what we should be able to do is just click test, and we can see that yes, this has succeeded. And if I went in and changed one of these rules, for example, to change one of these pin values here, then it would show me where that was not actually resulting in the right value. So what this effectively means is this should be working according to my rules, assuming I've got the rules right, and we don't actually have to test it in any other way. So if we just go back to our pin diagram, we can see that we've got pin 1 is E, read write is 2, then we go A15, 14, 13, 12, 10, 9, 8. Now, to start with, we are only actually using the 12, 13, 14 that we were using previously, so we don't need to wire all those in. So we just need to do 12, 13, 14. That's pin 4, 5, and 6. So I'll refer back to this diagram as we're doing it, but if we look now top down, if we zoom in a little, hopefully you should be able to see that better. Just get rid of the programmer here. Our power is off. So this is our decoder chip that we've got here at the moment, and we're just going to unplug this. Okay, so that's a decoder chip out, and I'll just look at how we're going to plug this other one in. So we are going to need to move some of the wires around a little bit, but fundamentally the pins aren't going to be too different. So let's just make a note of where these things are. So this is the E signal, so this may need to be a little bit longer. This one was the Y7 signal, so this was going off to the ROM here. So again, this might need to be straightened out a little. So I'll just move that out of the way there. And then this one is a serial port, so that's Y5, and this one was the peripheral interface adapter, so that's Y4. Okay, so if we can plug this chip in so that 4 and 5 are in the same place, we won't need to change those. So fortunately, the way how this has been labeled, we've actually got the output 0, 1, 2, 3, 4, all the way up to 7 there, so those will coincide with Y0 to 7. And so that means that 4 and 5 are plugged in correctly there. Okay. Need to make sure the pins are not too splayed out. Make sure our pin 1 is correct. Yep. And we'll then just plug in. Just check from above. So 4 and 5 are already in the correct place. These are enable lines that we needed to ensure were set to 0. So we're just going to wire in ground. So wired in ground. 5 volts VCC is still the same pin, so that's good. And that is Y1, which is going to the RAM up there, so that doesn't need to change. That's good. And then these are our address signals. Now our address signals are a different way around. So I think what we'll just do is take those out. So the only one we need to plug in here, this is Y7, which is probably a little bit long. 4, 5, 6. But just to get this working, we'll just bend it round a little. It's not the ideal way of doing it, but okay, I'll straighten that up afterwards. So that should be 5, 6, 7. And the only other thing we need to wire in here is our E clock signal. So that E is going to pin 1. It might in fact be better to take that signal from a little bit further over here. So we might just be able to squeeze that in there. And we just put this, clear out the stray bit. What? That E signal wants to go. There we go. We've got an E signal there. Now we also do need to do read write because we have included read write signal as part of the ROM, and that there. The read write is the next signal above that. So we make this just a little bit longer and go in over the top of it. So we'll make it just a little bit longer. And if we bend that over so there's a bit of a kink in it, a little higher, and this will allow a read write signal go into the pin beyond E. Right. We now have the two signals. So pin 1 is E, pin 2 is read write. Just check that against the diagram. Then we have ground 5 volts, Y1, Y4, Y5 and Y7, and we've included the read write because that is now used. Now we just need to remember to hook up the address lines. So we have down the bottom here A14, 13 and 12. Now the order here is slightly different from before. So A12 needs to be going to pin 6. That's pin 1, 2, 3, 4, 5, 6. A13 needs to be going to pin 5. And pin 14 needs to be going to pin 4. Now when we complete the memory map, to finish the memory map, then we'll be able to make those wires a bit neater. There's no point in doing that at the moment until such time as we do the 64K memory map. So let's just check we've got everything right. So we'll put the old chip away. That should be everything. So let me just move the camera back up so we can see the whole the project more easily. And I'm just going to switch on the bench power supply and see if we get, yes, we get a memory prompt. And if I go memory 1000, you can see that we're able to go through. So we successfully replaced our previous 74LS138 decoder, and we've now put our PLD in there. Now the advantage of this now means is that we can change our memory map and things much more easily. So in this video, we've now replaced the address decoder with our programmable logic device, and we've worked out how to program these and to burn them. In the next video, what we're going to be doing is to modify the memory map in the NanoComp so we can use all 64K of the address space, and that's going to require reprogramming the PLD and also changing the monitor source code so it will run in the upper part of the F800 memory range in the top of the ROM. So if you don't want to miss out on future videos, please hit subscribe, and if you found it useful, hit like. Thanks for watching.